All right, so we learned that Dmitry Mendeleev is responsible for these laws of periodicity, and we learned that he was the first one to make a thing called the periodic table of elements. So here it is, and you have it in front of you. So let me just bring up the next slide. The way this works is if you look up across the very top row, let me zoom in here. I can't zoom in very well. Well, if you zoom in and you look at the top of the chart, you'll notice that there's this row of thing called groups, okay? These groups are called 1, 2, 3, 4, 5, 6, and all the way through 8, okay? Those are representing columns, okay? So there's groups, those are the columns, okay? Then there are periods, those are the rows, okay? So there's like group 1, period 1, that's hydrogen, okay? Then there's like group 1, period 2, that's lithium, all right? Group 1, period 3, that's sodium, and so on, okay? So it's rows, it's groups, and it's periods, dividing it into rows and columns, okay? So let me give you now what that means for us. Each column, called a group, there's 8 groups. They move from left to right. This represents increasing atomic number from left to right. Each row, called a period, repeats the cycle of chemical properties. Okay? So the point is that if you look at group 1, period 1, that's hydrogen. Hydrogen acts like hydrogen, okay? Then you go down to the next period in that same group. Group 1, period 2, the one with an Li. Lithium, okay? Lithium and hydrogen will make the same chemical bonds. They act chemically the same, okay? Group 1, period 3, sodium. Sodium will make the same chemical bonds as lithium, which makes the same chemical bonds as hydrogen. Notice all of the ones in that column, that stack of elements in group 1, all act chemically the same, okay? There's going to be a good reason for that we'll get to in a little bit, but if you look at it, in group 1, period 1 hydrogen, period 2 lithium, period 3 sodium, and so on, are all going to act chemically the same as each other, okay? Group 2, so one column over, all of those are going to act chemically the same as each other, okay? So every column, every element in each column acts chemically the same, okay? So we go like that. Every group represents a column. Every element in that column behaves chemically the same, okay? Let's move on. I need to add on some more definition so that we can get the rest of this. Okay, so what have you learned so far? You've learned that atoms make up elements. The smallest, an atom is the smallest unit of an element. An element has some chemical property, and if you break apart an atom, its chemical properties won't be the same as the atom together. Okay, we learned that there's something called the atomic number, telling you how many protons in the atom, thereby telling you how many electrons orbit the atom, and how it'll behave chemically. You also now learned that we've grouped the atoms up into a table, a periodic table, separated into groups and periods. Every column, every group, is going to act chemically the same. Okay, so on the totally right side of it, group 8, helium, neon, argon, krypton, xenon, and so on. The group 8, they all act chemically the same. Everything on that very right column acts chemically the same. So that's the story with the periodic table. The next thing I need to get out to you guys is, so we've talked about protons and electrons so far. I need to now get out to you that there is another particle in the nucleus, okay, that is massive, but not electrically charged. Okay, so it doesn't change the chemical properties of an atom. It just changes the weight, the mass of an atom, okay? This next particle is called the neutron. Interestingly, predicted by Rutherford and if I'm getting my history right, it was discovered by one of his graduate students. This is how physics sort of works, right? You discover something, and then you teach new people, the next generation. Those next generations discover the next important thing, okay? Predicted by Rutherford, discovered by, I think, by his student, with a mass slightly heavier than the proton. But for our purposes, we just call it an atomic mass of 1. It's a little heavier, though. The the mass of a neutron is basically a proton and an electron bound together. Okay, so it's 1 proton in weight plus 1 electron in weight. Okay, and what do you know about protons and what do you know about electrons? Electrons have a what kind of charge? Negative. Negative, not just negative though. Negative 1, right? And protons have what kind of charge? Positive, but not just positive. Plus 1, right? So if you put an electron and proton together, then you get plus 1 minus 1, which is 0 or nothing or neutral, right? No electric charge. So that's what a neutron is. It's combined. It's a combined thing. It's a proton electron pair, okay? Making this thing called a neutron. Electrically neutral. This is why it was the last thing to be discovered, because it's electrically neutral. It doesn't play well in electric and magnetic fields, but it's electrically neutral, and it can be thought of as being a proton-electron pair. Interestingly, there's actually one other little particle that we're hiding from you called an antineutrino. There are other particles. There's a whole bunch of particles that we're not talking to you about, and there's another particle locked up in here that we're not going to talk to you about called an antineutrino. But just so you know, there's always another level down, okay? That was something that wasn't really relayed to me as a student. Yeah.
I understand why we need to understand barium, but all the other ones that we have to, calcium, aluminum maybe for the machine.
Yeah, filter.
Like
yeah.
Do we have to memorize it how it is on the table, or kind of like just because we're going to be using it to like make barium for them to ingest?
Yeah. So really, it's just so that you can have the picture of in your head of how atoms work, right, and the relative weight of the atoms compared to others, right? It's not that you're going to be using all of these every day. It's just that as a radiographer, you should have a good idea of what makes up the thing that you're radiographing. Plus, when we consider how the X-rays interact with materials, right, we have to understand that the denser materials the X-rays are going to be absorbed by, the lighter materials let more X-rays through. So it helps us understand our images too. So there's a good reason to understand all of this. The level you should understand it at is you should understand the name of the important atoms, what their atomic number is, and then from that be able to figure out their electron configuration, which we haven't talked about yet. So you should be able to do all of that, and those are expected. You should be able to be expected to answer questions about them on tests and things. So they just said that's part of what an X-ray tech should know, because it affects how X-rays interact with those materials. We work with those materials, right, lead and so on. So yeah, that's sort of good reasons why. But you don't need to know all of them, though. That's right. So this whole periodic table, I will never ask you to memorize the whole thing. I'll ask you to know some of the important ones from it. I don't bother remembering. I can remember aluminum, but I don't worry about it too much, right? I remember tungsten and lead and stuff like that because I need to. Carbon, oxygen, helium, hydrogen are pretty easy, yeah. So just a few of the important ones. And then, pretty much you can go to a periodic table and look it up when you need to. I always remember this one thing that Einstein said. He said a lot of smart things, but one thing he said was to a reporter who asked him, some reporter asked him some answer to some stupid, simple question, some stupid physics question, and he said, paraphrasing him, I don't bother remembering something if I can just look it up in a book, right? And this is, you're talking about Einstein, one of the smartest people ever, right? He said it in a smarter way, but basically, if I can look that up in a book, I'm not going to worry about sticking it in my brain, right? I got other things that I'm using my brain for right now. So that's sort of how I think about this stuff. You got to memorize and stuff a bunch of it in your brain to get through testing and things like that. But after that, no one's going to keep you from going into a book and looking it up. So work on it for our purposes and learning the curriculum, being able to pass tests. And then later on, you can just go back to your periodic table if you ever need it. Yeah. Okay, good. So neutron. Another particle in a nucleus. Now, there's no relationship between how many electrons orbit at the atom and how many neutrons it has. There's nothing that says how many neutrons an atom will have in that way. There's also no relationship there's not a one-to-one relationship between protons and neutrons. Some atoms have more or less neutrons, some atoms have none, okay? Neutrons are one of the possible nuclear particles. Neutrons in a nucleus are held together. Do you guys remember there's 4 forces that nature has, right? The weak force, the strong force, electromagnetism, and gravity, right? Which of the 4 did we say is responsible for holding neutrons together? That's the one that's responsible for holding protons together. So then what's the other nuclear force? The weak one, right? That's the one responsible for this, okay? If you take a neutron outside of a nucleus, guess what? The weak nuclear force isn't doing its job anymore, right? And so neutrons are unstable. If they're removed from an atomic nucleus, they will decay, and they'll decay in a way that emits something called a beta ray. You guys have learned about beta rays in radiation safety, right? It's one of the possible radioactive decays that atoms have, beta rays. And now you're learning why, okay? Neutrons are unstable and occasionally break apart. When they break apart, they emit a beta ray. In secret, a beta ray is really just a fast-moving electron being shot away from an atom. But we call it a beta ray. We call it a beta ray because alpha rays were discovered first. Alpha, beta. Okay. So to summarize what we just learned, we use the Bohr's atom to picture Bohr's model to picture an atom. It's pictured as a dense, massive nucleus with both protons and neutrons in the nucleus. The number will vary according to the element. 99.9% of an atom's mass is in the nucleus, which is very far away from the orbiting electrons. Small, lightweight electrons are orbiting in specific, discrete orbits. Okay, and that's our model. So what we need to go do now is we take everything we just learned, and now we need to learn why atoms have the chemical properties that they do. You know, when you look at the periodic table, right, you know, why is everything in this first column, you know, helium, lithium, sodium, and so on, why do they all behave the same? Okay, what is causing them to all behave the same? Because if you look at the top left corner of each square, hydrogen has a 1, lithium has a 3, sodium, Na, has an 11. That's the atomic number. That's telling you how many protons are there. So they're not the same size, even a little bit. Hydrogen has 1 proton, lithium has 3, sodium has 11, but they act chemically the same. So we're gonna have to learn about why that's the case, okay? So strap in, please. We gotta learn some important rules, okay? And so electrons arrange themselves according to these 2 specific rules, okay? With these rules and knowing the atomic number, you can figure out the electron configuration of any atom, okay? So here's the rules. First rule, the maximum number of electrons that can occupy a shell under any conditions is given by the formula 2n squared. N is the shell number. So what do we usually use to name the shells? Numbers or letters? Letters. We K, L, M, N, O, and P, right? Replace K with 1, L with 2, M with 3, and so on, okay? Give them numbers instead of letters, all right? The number of the shell that you're talking about, that you want to figure out, you put that where the N is, okay? So if I want to know, let's look at oxygen. Oxygen, well, it's
8.
Z number, right, equals 8, okay? Good. Z number equals 8. So we know there's going to be 8 protons and 8 electrons. We know that about oxygen so far, okay? We don't know how many neutrons an atom of oxygen would have. It can change and vary, but don't worry about that right now. We're going to use the 2n squared rule to figure out how many electrons can fit in each of these shell levels. Okay, we need we have 8 protons, so we're going to need to account for 8 electrons, right? The K shell equals 1. The L shell would be 2, and the M shell would be 3. Okay? So using our 2n squared rule, 2n squared, we're going to put, if we're going to figure out how many are in the K shell, the innermost shell of oxygen, then we're going to put a 1 where the N is. So 2 times 1 squared. How do I work forward from this? I use my order of operations, right? PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. This is telling you the order in which to do your operations, right? The order in which to do your steps. So, are there parentheses? Yes. Is there an equation inside of the parentheses? No. Good. So we don't need to do anything with the parentheses, right? So what's after P?
Exponent.
Exponents, E, right? Is there an exponent? Yes. Here, squared. I'm squaring something, right? What am I squaring? I'm squaring what's inside the parentheses, right? So I'm taking 1 and squaring it. So 2, there's really, by the way, there's really a multiplication sign between these, but we just drop it in math equations, but I'll put it back. 2 times 1 squared. Well, what's 1 squared?
1.
And how did you figure that out?
It's 1 times 1.
1 times 1, I know. I don't know that everyone can do that, right? So I gotta make sure. So 1 times 1 is 1, so 2 times 1, okay? What's 2 times 1? 2.
That's good.
2. Okay? We can put an equal sign if we want to. Right? But 2. 2 is the answer. Okay? So, how many electrons can fit in the K shell of any atom? 2. Okay? So let's draw oxygen here. We're going to put plus 8, showing the nucleus. And then we're going to put 2 electrons. Okay? How many more electrons do we have to account for in oxygen? 6 more, because we've accounted for 2 of them so far. Okay? So let's do this formula again, and let's figure out how many can fit in the L shell. The L shell has a 2, so 2n squared. I'm going to replace the n with a 2, so 2 times 2 squared. Okay? Order of operations tells me what?
Multiplication.
Parentheses, exponents. So parentheses, is there an equation inside the parentheses? No. By the way, just always do the full PEMDAS. Don't skip, okay? You're going to mess things up, okay? So you just ask yourself, is there a parentheses? Yes. Is there an equation inside of it? No. So move on to exponents. Is there an exponent? Yes. Here. What am I going to be raising to the power of 2? I'm going to raise 2 to the power of 2. 2 squared, or 2 times 2. What's 2 times 2? 4. So 2 times 4? 8. My answer to how many electrons can fit in the L shell of any atom is 8. We're going to apply this to oxygen, but this is how many can fit in the L shell of any atom. Okay? 8. So I'm going to make another shell. How many can I fit in that shell? 8. How many are going to be in this shell? 6. Okay. And we're done with oxygen. Okay. So oxygen only has 2 shells. Or rather, oxygen has 2 shells because of the 2n squared rule. We can fit only 2 in the innermost shell. Okay. And that's going to be for any atom. Any atom can only fit 2 electrons in its innermost shell. in the case of oxygen, it fits 2 in the innermost shell, and so we need to account for 6 more to make 8. Our second shell in any atom can fit up to 8, and we only need room for 6. Okay, so we put 6 in the innermost, in the second shell, which this second shell is now our outermost shell of the atom. We're done now, right? Okay, so then we need to learn the next rule. The next rule. The outermost shell, whatever shell number that is, in this case it's number 2, okay? But you saw barium, right? Barium had a bunch of shells, okay? Whatever the outermost shell is, doesn't matter which one it is, it's going to follow a rule called the octet rule, okay? This is the important one. The octet rule says the outermost shell of an atom, no matter what the 2n squared rule says it can do, the outermost shell can only ever hold 8, okay? And not just that, 8's the maximum for the outermost shell, but if it has less than 8, that atom is going to try to bond with any other atoms that it can so that it can borrow as many as it needs to get to 8. Okay? So look at oxygen. It has 6 in its outermost shell. Using the octet rule, how many can it hold? 8, okay? Which, by the way, also happens to match with the L shell's maximum, but that's just a coincidence for right now. So there's no deeper explanation here. But 8 is how many it can hold, and not only that, 8's how many it wants to hold, okay? So this is a neutral oxygen atom. It's electrically neutral. It has 8 positive and 8 negative charges, but it's still going to seek out a bond with any nearby atoms that can give it up to 2 more electrons to make 8 in the outer shell, okay? So let's do another one. I'm going to put a line here, okay? And let's do hydrogen. Hydrogen's Z number is? Top left? 1, okay? So that tells us 1 proton, 1, I'm just going to write electrons with an E, a little negative sign next to it so I don't have to write the whole word. 1 proton, 1 electron, okay? Good. So now let's do the same thing, okay? How many electrons does hydrogen need to have? 1, okay? So let's do how many can fit in the K shell of any atom? It's shell number 1, but it can fit 2, okay? So we'll say the K shell can hold 2, okay, 2 electrons, okay? But in a hydrogen atom, plus 1 nucleus, it's only going to have 1 orbiting electron, okay? This hydrogen's a little weird because hydrogen only has 1 shell level, okay? It's going to use, it's going to try to get another 1, okay? 1 more. If this hydrogen atom happens to get near this oxygen atom, it can partially lend its electron to oxygen, okay? Oxygen gets to have the electron, the extra electron, okay? Hydrogen gets to share this electric charge, this electric attraction, okay? And so now how many electrons are orbiting around oxygen? 7. That's more than oxygen, sorry, in the outer shell. 7, you're still right, 7 in the outer shell, okay? And how many is the outer shell supposed to hold? 8, okay? So along comes another hydrogen atom, which also lends one of its electrons to oxygen, okay? Making water, okay? Water is chemically stable because the hydrogen atom is trying to borrow a single electron, okay? Oxygen is trying to borrow 2 electrons. So each hydrogen atom wants to borrow a single electron, and the oxygen atom wants to borrow 2 electrons. So you need 2 hydrogen atoms to make the oxygen atom happy, and each oxygen atom gets to borrow part of the time one of the electrons from oxygen to make itself happy, to make its inner shell have 2. Okay, so they bond up very well together. Okay, so you can also do that with, if you look at lithium. Okay, lithium, its atomic number is 3. If you look at your periodic table, lithium's atomic number is 3. So how many electrons will be in the inner shell of lithium? 2. So it needs another shell level, right, to account for the third one. So there will be a second shell for lithium. How many electrons will be in that second shell? 1. Hydrogen's only shell is its outer shell. It has 1. Lithium's second shell is its outer shell, and it also has 1. The fact that the outer shell of lithium and hydrogen only have 1 electron is why they're in the same group. Okay? What you're looking at in the group is the number of electrons in the valence shell. Okay? So everything in group 1, that whole left-hand column, has only 1 electron in the valence shell. Okay? If you look at the very right side, group 8. We call group 8 the noble gases. Okay? Group 8 has the property that its outer shells are full. Okay? If you look at neon, for example, what's neon's atomic number? 10. Good. How many electrons will be in the inner shell of neon?
2.
Good. So how many do we have left over? 8. How many can fit in the second shell of neon? 8. Using the octet rule, how many can the outer shell hold and be happy? 8. Okay. And how many do we have to account for? 8. Okay. Meaning that neon's outer shell will have 8 electrons. The octet rule is satisfied. The atom will not seek out a chemical bond because it has a full outer shell. Okay? Make sense? Yeah. So neon won't interact with any other atoms, generally speaking, because it's full. Okay? That's why they call them noble gases, because they're full. They don't need you. Okay? They don't need to interact with other atoms. I'm steering clear of the middle of the periodic table because it gets a little complicated in the middle, okay? You notice how I spent most of my time on the left column or the right column, but the rules still apply. Like if you look at column 3, group 3, or the third column, everything in there, right, which includes aluminum and titanium in there, everything in there is going to have the same number of electrons in the outer shell. It's going to be 3 electrons in the outer shell, meaning all of these in group 3 are going to try to grab onto 5 electrons. However many atoms it needs to link up with to get those 5 will be different. That's all of chemistry, okay? But the point is that everything in column 3, all of those are going to have 5 unused spots in their outer shell that are going to try to get filled with chemical interactions with other atoms, okay? All right. So, by the way, you can just sit down and do the 2n squared rule and figure out how many in principle can fit in any given shell, but let's just give it to you, okay? This is how many can fit in any given shell. Not, importantly, not how many will be there. That's determined by the atomic number, right? This is telling us how many in principle. This is why we also call it the principal quantum number. It's telling you in principle how many electrons can fit in a shell. So the K shells can only ever hold 2. So you'll only ever find 2 electrons in a K shell of any atom. The L shells can hold 8. M is 18. N shell 32. O shells up to 50. And P shells up to 72. Okay. If you had full shells for all of these, you can add it up and see how big the atom would be. Okay. We typically don't need all of these shells full. All right. Now, if the P shell were the outermost shell of an atom, it wouldn't be able to hold 72, right? It would be able to hold 8, right? If the O shell was the outermost shell of any given atom, then it can't hold 50. 8's its maximum. Remember, the outer shell, the valence shell, no matter what the 2n squared rule says, the valence shell will always and only ever hold 8. If it has 8, the atom's full and it's a noble gas. If it has any less than 8, it's going to try to get as many electrons as it needs by making chemical bonds to get to 8. That's the octet rule. So the octet rule matters for telling you how many electrons are going to be unpaired in the outer shell and how the atom's going to interact with other atoms, either will or won't, right? And the 2n squared rule is going to give you an idea of how many electrons you can find in principle in any shell using 2n squared, the octet rule, and knowing the atomic number. You can figure out electron configurations for any atom, okay? You guys, I'm not going to give it as a homework assignment, but I recommend if you want clarification with this, you need to just sit down and do each atom, okay? I've done it. Once you sit down and do each atom, one by one, you'll get a much better idea of how this actually works in practice. But I won't make you, because it's not part of our necessary stuff. It's just necessary that you understand the rules that we're playing with here. Okay, questions here? All right, I know that's complicated. I know that's a lot. The book actually does a really good job of simplifying it down to just these 2 basic rules. So these 2 rules, along with knowing the atomic number, will tell you what the electron configuration is of any atom that you like. So let me just restate what I've said. Chemical behavior of atoms is determined only by the number and configuration of electrons in the outermost shell. So for chemistry, we care about the outermost shell. For chemical interactions, the outermost shell. The outermost shell is filled by the octet rule when there are 8 electrons in it. Neutral atoms with 8 electrons in the outer shell have no tendency to interact with any other atoms. They are considered inert, and we put them in the rightmost column and call them noble gases. Why are they gases and not like noble solids? What do solids have to do? How do solids have to behave chemically? The atoms of a solid have to break down? The opposite. Build up, right? The atoms of a solid have to connect, right? Remember Dalton's hook and loop idea, right? He thought the hook and loop idea because atoms had to be a solid, or things had to be, we had to account for solids, right? Noble gases are gases because they don't make a bond. They are not going to link up with themselves. Take a container of neon, right? It's no matter what you do and how much pressure you put onto it, those neon atoms are not going to come together to make a clump of neon, okay? The atoms are inert, noble gas, whatever you want to say. They're not going to chemically bond with each other. Okay. That does a good job of explaining electron configurations. Okay. So let's now talk about, we've done a good job with that. We're about halfway through the notes, so I just don't know that I'm going to get it all today, but let's do our best. Now we need to talk about chemical bonds. So we learned that the chemical bonds are to do with the outermost shells of atoms. And so we need to learn that there are 4 types of chemical bonds. These are called covalent, ionic, proton bridging, and van der Waals forces. The most important are going to be your covalent and ionic bonds, but these others we'll work with. Oh yeah, here we go. Only covalent and ionic bonds are of particular interest for radiography. So we're going to talk about all 4. We should be familiar with the first 2 though. Both of these involve, covalent and ionic, involve exchanging outer shell electrons, exchanging or sharing in such a way that they spend time around both atoms. We can think of them as orbiting in like a figure 8. The electron goes to one atom and then comes back to the other and then goes back to the other one. They're spending time. It's kind of like a, co-parenting or something, right? The electron has to go back and forth between atoms. Okay. To talk about covalent bond, I need to go back a little bit to the orbitals that we were talking about. So just bear with me for the orbitals. So remember that the shells that we show you with Bohr's model is not how atoms actually look, how they're actually arranged. It's just a colorful way of talking about it, okay? Electrons actually exist in what are called orbitals and suborbitals, okay? So within an atom, each electron shell, and we know that shells can hold many electrons, right? There can be many electrons in one shell. So each shell is broken apart into subgroups called suborbitals. Each suborbital of a shell can hold 2 and only 2 electrons. Electrons spin like a top, okay? But unlike a top, when electrons spin, well, let me backtrack a little bit. What do we know about electrons? What are their properties? What's one property of an electron? It's negatively electrically charged, and it has some mass, right? 1/2000th of an atomic mass unit, right? But the important part of this is exactly what you said. It's got an electric charge, okay? So those of you who have been with me for a while, think way, way back. What happens when electric charges move? We won't say that. That's maybe a little vague, but when electric charges move, magnetic fields are generated, okay? These electric charges, these electrons, have intrinsic electric charge. It doesn't go away, okay? Like a battery can die, right? But an electron that's built into it. The fabric of an electron is built in that it has an electric charge. Let me rephrase. It's what we call a conserved quantity. It doesn't go away, okay? So electrons have an electric charge. We know that when electric charges move, magnetic fields get generated, okay? That's how all of your electric motors and anything you have that has an electric motor works. Hair dryers, cars, things like that. Okay? Anything that has an electric motor uses this principle. Electric charges move. Moving electric charges generate a magnetic field. Magnetic fields always have a north pole and a south pole. Okay? Electrons spin. That's a form of movement. Okay? And spin is a conserved quantity for electrons. All electrons spin. Okay? Meaning that all electrons have a north and a south pole. In a suborbital, in order to make things equal, there have to be 2 electrons spinning in opposite directions. They have to have opposite spins, okay? So you can think about an electron spinning as like wrapping your hand in a direction, okay? Your fingers represent the direction of spin, and your thumb represents the direction of, let's say, the North Pole, okay? So if an electron is spinning this way, we'll say it's spin up, okay? If an electron is spinning the opposite direction, the North Pole will face the opposite direction, down, spin down, okay? In these suborbitals, there will be 2 electrons, magnetic north and magnetic south pole. Each electron has one, and they have to be opposite, okay? So let me say this. When there's an even number, so like this suborbital has 2 electrons, it's happy. This suborbital has 2 electrons. The north and south magnetic poles cancel each other out. Everyone's happy. Each one of these suborbitals, in this case, has an equal number of electrons that are opposite in spin. With this, when there's filled orbitals, there is now an equal amount of negative charge around the entire atom. The atom is equally negatively charged around the whole outside, giving it that negative screen of charge and now allowing the atom to bump up against things and not bond with it, okay? However, if one of the suborbitals is missing an electron because the atom has been ionized, right? Or it's an incomplete valence shell, like hydrogen, right? Hydrogen is missing 1, right? So its orbital will be only having 1 electron, and it's spinning in only one direction. And so we've got an imbalance in electric and magnetic repulsion charge. When there is an odd number of electrons in the outermost shell, there must be 1 orbital that contains only 1 electron. That's what it means to have an odd number, right? They want to pair up, and anytime things are in pairs, we can only have even numbers. So if there's an odd number of electrons, and you'll know if there's an odd number of electrons because you'll learn the octet rule and the 2n squared rule and the number of positive and negative charges. You'll know how to tell if there's going to be an atom with an odd number in the outermost shell. By the way, you don't even have to do that. You just go to the periodic table and look at any of these ones, okay? Any of these atoms, except for, you know, the rightmost column, are going to be missing electrons, okay? Missing electrons in the outermost shell. Since this odd number cannot be evenly distributed, a slightly more positive area on the atom will appear. We call it a hole. We'll use that hole talk later in much later lectures. But now you've got one part of the atom that is a little bit more positively charged than the rest of the atom, okay? Giving the atom a dipole of electric charge, meaning that it's going to have a difference in electric charge from one end to the next, okay? If you imagine just drawing a line across the atom, that's a terrible color, but you can imagine drawing a line across the atom, right? And the top hemisphere of the atom has a little bit more positive charge than the bottom hemisphere, okay? Making it now an atom that's got positive charge, negative charge, okay? Okay. Through this defect, this net tiny amount of positive charge, the positive pull of the nucleus can now be felt by outside electrons or atoms. Some nearby atom and its electrons are going to be pulled on by the nucleus of this atom. Okay? The two atoms may now stick together and share their unpaired electrons. This is covalent bonding. These two unpaired electrons will spend time around each atom. They will go back and forth between atoms, spending time around each, creating the appearance, for all intents and purposes, that each atom is full, but they're only full because they're borrowing each other's electrons to fill up. Okay? To fill that tiny amount of charge difference, it's going to have to grab onto a nearby atom. This is a bond between two atoms sharing valence electrons. Covalent bond. Okay? Covalent bonding is the most common form of chemical bonding between atoms. Now it makes sense why covalent bonds happen, because the octet rule says we need to fill our outer shell with 8. We learned why the outer shell needs to be full of 8, because of these suborbitals and the opposite spins of electrons and the electrons having to be paired up, right? So we learned that there's a reason why, but the point is that anytime there's an outer shell with an odd number of electrons, it's going to have to grab onto anything nearby to equal out that difference in charge. Covalent bond. The other type, it's called ionic bonding. An ion is any charged particle or charged atom. So an electron out in space by itself, that's an ion. An atom with an electric charge all by itself, that's also an ion. Okay? An atom may become a negative ion with a charge of -1 if it remember, electrons have a -1 charge, right? So if you're a neutral atom and you happen to grab onto one electron momentarily, then you're an ion. You're a negative ion. An atom can be a positive ion if it loses an electron. What do we do in radiography that might cause atoms to lose electrons? What can X-rays do to matter? Ionize it, right? And now you're learning the word ion means a charged particle. You learned that ionization, if you know the word, you learned that ionization means creating charged particles, right? Creating ions, okay? If an X-ray photon kicks out an orbiting electron, you've now created a positive ion. In fluids, for example, Negative and positive ions will move toward each other. What's a fluid? What is the definition of a fluid? Is my coffee a fluid? Is the air in this room a fluid? My coffee's a liquid, right? Liquids are types of fluids. Gases are also fluids, okay? If you take a fluid mechanics course at a college level, you will learn about gases and liquids. They are both types of fluids, okay? The rules of fluid mechanics work for gases and liquids. Fluid does not mean liquid, okay? We use it to mean liquid sometimes, but fluid means gases or liquids, okay? Not solids, okay? In a solid, like if a solid tabletop here, if there's an ion, a positive ion over here and a negative ion over here, are they going to get to each other? No, right? The molecules over here are only ever going to be over here, okay? And the molecules over here are only ever going to be over here. But in a gas, if I've got a positive ion here and a negative ion here, and the rest of the gas is just neutral, then those two ions are going to feel each other's pull. The further apart they are, the less they pull, right? But there's a pull nonetheless, okay? And they're going to feel that pull. And in a gas, they can move around, right? Freely floating particles can move around. Same thing in a fluid, right? Two positively charged particles, or two charged particles, positive and negative, in my cup of coffee, right? They can move toward each other because they're in a fluid, right? Fluids, the particles in fluids can move around. Gases and liquids are fluids. Okay, so yeah. Once they contact each other, the positively charged atom, which reminds you is missing an electron, will steal or take the spare electron from the negative atom, forming a bond. Okay? It's just going to borrow it, but the atom's not going to let it go, so they're going to bond up together. Okay? Making an ionic bond. Covalent bonds are short distance. The atoms have to be very close together. They basically have to bump into each other, okay, by chance. Bonding then occurs because of the flaws in the regional distribution of electric charges. At a distance, the same atom appears electrically neutral. No force is experienced at a distance. However, ionic bonding is a long-distance phenomenon when whole atoms feel the strong pull of the electrical force even from a distance, okay? And again, in a solid, this won't happen, but in a fluid, this will. Okay, so liquids are gas. Okay, excellent. So we now have covalent and ionic. And we're just not going to worry about the other two. Okay, our other two types of chemical bonds, proton bridging and van der Waals forces. If you want to learn about van der Waals forces, go look up geckos. Geckos use van der Waals forces to climb walls and stuff. It's kind of really cool, actually. But I don't have time for that. So I'm going to move on. There are too many cool things in this world to talk about, so I can only get to a few of them. All right. Next is ionization. So let me actually pause my recording.